The broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon or good morning or even good evening, depending upon where you are in the world. My name is Claire Francis from Scientific Update, and I'm going to be your session moderator this afternoon for today's webinar on a journey of a catalyst. Just before we get started, the usual administrative points. We are recording this session and I'll share this together with the slides that Akim is going to present via email. This sometimes does go into people's spam folders, so I just recommend that you have a look in your junk folder if you haven't received it later this evening. If you can't find the email from us for any reason, then we're also going to share the slides and the recording on our webinar archive area in our website, so please look there. If you have any questions for Akim, if you could use the questions area on your GoToWebinar dashboard and type those in, I will try and ask him at the end. He says he has about 50 slides, maybe a few more if we have time, so hopefully there'll be some time at the end for some questions. So it's my great pleasure to introduce you to our speaker, Akim Link. Akim has an MSc and a PhD from the University of Basel, and then he's also spent some time working with Professor Buchwald at MIT before he joined Solvius in 2020 as a project leader. He currently leads the Catalysis team, and he's going to give a presentation to us called The Journey of a Catalyst, Catalyst on Scale, Development of an Iridium Crabtree Phelps type catalyst for asymmetric hydrogenation. So I'll hand you over to Akim now. Thanks, Akim.
Thank you very much, Claire, for this kind introduction. Yeah, I'm happy to be here today and present you the journey of a catalyst. I will just stop my camera. Yeah, so the journey of a catalyst. It's a story about developing how to develop a transition metal catalysis to enable a multimetric ton scale production of a key building block for an agrochemical. And this was done and driven by the investment of our customer, Bayer Crop Science, together with Solvius, and then by Bayer initiated industrial academic collaboration with Likat Rostock, the laboratory of Matthias Beller. The asymmetric hydrogenation of this dihydroquinoline structure, in which the double bond is highly sterically hindered and not directly functionalized, significantly limits actually the freedom of choice or the chance to identify a commercially available catalyst. Well-known catalysts for this kind of asymmetric hydrogenation of such unfunctionalized, highly hindered olefins are actually the iridium Crabtree Phelps type catalysts. So there was some indication where to start developing that type of asymmetric hydrogenation. A challenge in agrochemistry is always actually to achieve the desired price range for such chemicals, which are in the one max lower two-digit dollar range per kg, which is in contrast to API molecules that are often more complex, but still also the price there is probably between $2,000 to $5,000 per kg, highly complex, even greater than $20,000. So here we really need to develop a highly competent catalyst to achieve an asymmetric hydrogenation on ton scale. And this in order justifies the investment. I'd like to start actually with who Solvius is. So Solvius is a CRO/CDMO, Swiss-based contract research organization, founded in 1999 as a contract as a spin-off from Novartis. In the meantime, we are owned by two American investors, Water Street and JLL, grown over recent years immensely to 800 employees. We are ISO and GMP certified, successfully FDA inspected. A large part is actually located in our headquarters in Kaiser-Augst, the suburb of Basel. There's a big part of our analytical services. Then in Basel, where the Catalysis ligand group and small molecule GMP production is located. In recent years, several companies have been acquired. Homburg, France is focusing on large biomolecules. Utrecht, Netherlands, they are experts for DNA and RNA technologies. And in Canton, Massachusetts, also analytics, but we are also ramping up their GMP small scale production for early phase and clinical phases of API. Overall, Solvia's capabilities are shown here. Different experts group working closely together. On the left side, you see the area where I will talk mainly about today: custom synthesis, ligands, and catalysis, and involves certainly also small molecule analysis, polymorph crystallization screening, and to some extent we are also closely together with elemental and trace analysis. The other parts I won't talk today, but in case there are questions, we are happy then to make connections to the experts in case you are interested in these analytical fields. Integrated solutions for early phase development means that these different expertise groups working closely together form the discovery and route selection to the catalysis, developing a catalytic step, and identifying the right ligand, or even like today shown in the story today, shown a customized catalyst or ligand, then process developing, scaling it, manufacturing it, included also solid state and our analytical experts, and this assures a high quality, speedy for complex small molecule APIs early phase, but we can even go beyond that. The high expertise in our groups actually also not only enable such an appropriate phase-appropriate development in kg amounts for GMP production for clinical testing, but also developing then systems further, catalysis and ligands, and this is shown also in collaboration with an academic group where we produce a tailor-made catalyst for our agrochemistry, and we profit there in the catalysis service. So our catalytic group actually profits from highly long-term experience in this area. This was once Ciba-Geigy Labs, then became Novartis, and then Solvias, and these experts are actually still active as consultants, retired now, but they partly also shaped the field actually of asymmetric hydrogenation and other transition metal catalysis. But we also have young chemists that bring innovation from MIT or Princeton, Macmillan Lab, for example. We have project leaders that then also bring in the newest fields like photoredox chemistry, for example, or hydrofunctionalization. In the screening, we actually can exploit an extensive catalyst and ligand library. We have a catalyst and ligand catalog that's around 150 ligands and catalysts, but beyond that, we collected over the last 3-4 decades a huge library also of research type ligands, and our ligand group is highly experienced and also scaling and developing this in case there's no commercial already on kg amount scaled ligand or catalyst available on the market. We have speed. We do targeted high throughput screenings for lead identification on our high throughput screening robot by combinatorial screening under ideal conditions in the glove box. We are investing in new equipment also there to further accelerate automatization, by automatization accelerating our project, making them very cost effective. And we are then also able to scale, do optimization QA studies and scale up to kg amounts, also in pressure equipment, for example. And our expert teams, as already mentioned, are closely integrated, working together from catalysis, analytics, ligands, project R&D, synthesis, GMP production, then and the solid state group. Our high throughput robot, we are able to screen different kind of conditions by combinatorial screening already mentioned. This gives us really the chance we combine metal sources with this large ligand library for individual in situ formation to leverage this unique ligand library. So this goes far beyond the commercially available ligands. Doesn't mean that once one catalyst is identified in the lead identification that we don't then preform this catalyst to make it even more effective for your process. And we focus there on 96 well plates. It can do high pressures and many reactions a day and have then automated HPLC and GC analytics available. We will upgrade our system. We get a new HCS platform. There we also got OSR reactors, optimization sample reactors. These are 50 milliliter autoclaves where I can do in situ sampling under pressure, automated, fully automated. We have extended powder dispensing, which increases flexibility to then put more than 1,000 catalysts actually in our fully automated library storage. To automate the screenings further. We don't do only asymmetric hydrogenation. Heterogeneous we have experience for highly selective processes, but also homogeneous hydrogenations of different functional groups, CO, anamides, imines, CC couplings. Besides that, we certainly do cross coupling, CN cross coupling, CC, also atoposelective CC, highly challenging couplings. Then carbonylations under pressure, as well as reductive amination. We have a collaboration on biocatalysis with Enzymicals. That's a German-based company, and we do also chiral resolutions, also often for aqueous salt resolutions on the plate to identify racemic resolutions, and in some to some extent also dynamic kinetic resolutions. So yeah, with that, I covered our expertise and come back to Tobias' quest, the production of this herbicide in pyrofluxam. Yes, so and this was taking place over quite some time, starting in 2017 already. Over 6 years, this investment was taken, and yeah, it's about the asymmetric hydrogenation of this highly hindered olefin. There was some state of the art. There was already a patent application filed 2015 by another company, and they found actually yes, iridium uvafox works to some extent, but you see low conversion, 14%, 30% EE. And this was the point by our brochures. We did an expertise screening, and you see the value of an expertise screening led to first hit that then enabled us to develop this chemistry further over the last 5 years, significantly lower the catalyst loading, and by this make this a feasible process for then production. Yeah, one challenge actually for iridium catalysis is certainly the price, and you see during that time the price went up significantly, and this was actually yeah, it happened during the as you can imagine, during the COVID pandemic. You see this rapid price increase, and yeah, so that's such a price increase is not necessarily important for medchem, right? You just need small amounts. You may make kg amounts in the beginning, but the more you scale your product, the more important it comes. And for agrochemistry, certainly is then important, and certainly a point of concern. And what happened here in the beginning of 2020 is actually that one single iridium process facility in South Africa was closed due to COVID, and yeah, that's such a price spike is highly concerning, considering supply chain and supply chain security. And yeah, actually price determining for this transition metals it's not a fine chemical industry, it's rather the car industry. They use huge amounts of these metals as in automotive catalytic converters. And on that, here you see added additionally the rhodium price development over the past years. Yeah, this immediately increased after the diesel scandal used to reduce nitrogen oxide pollution. and then a second spike here, then 2021, caused by the ramping up again of the car industry, raising output after the global chip shortage was actually started to ease. Price is always formed on availability and demand. Rhodium, for example, is just actually mined as solely as a co-product of other metals that are mined. And if you imagine you have maybe a 0.1 gram to maximum 0.5 grams per ton ore that can be actually isolated. So it's quite a challenge to enable production of such molecules that societies need of this transition metals. So it's very important that you have a fitting catalyst. So two strategies enable still using this metals. So one strategy might be to use less costly transition metals, but they are often not as competent. But we are also going in investigating in this area. Another strategy is what I'm talking today mainly about, is reducing the catalyst loading by really having a tailor-made, customized, competent fitting catalyst for your substrate. And this then lowers the cost in such a way that then catalysis on scale is possible with these metals. Certainly also the metal can be recycled to some extent. So why Bayer approached us? Certainly they were aware of our competence in the field. In our catalysis lab by Felix Spindler, who is still a consultant in our group, developed the metolachlor process from the 80s to mid of the 90s. At that time it took a bit more, 12 years R&D, and it was an asymmetric imine hydrogenation, also iridium catalyzed with a diphosphine ligand. At that time, this development then justified the investigation and development of this whole ligand family. That's now a big part of our ligand catalog. And they were able to achieve this asymmetric hydrogenation. ER was not as good, but not as important for agrochemicals as in pharma. But they found then conditions, actually a process where they could optimize and achieve a substrate to catalyst ratio of 2 million. In 5 years now, with our process, we reached 25,000, which then is at the moment enough to have a very economical process. Just as a little information on the side, some of us are rather used to mole percent as a scale for catalyst loading. So here I have the S to C 1 mole percent corresponds to S to C of 100, and then 10,000 001 mole percent, and so on. And this means that, for example, in this metolachlor process with this loading, they can reduce actually 10 tons of this imine here with just 33 grams of iridium cod chloride, the metal precursor, and 68 grams of the ligand. And this is done on scale, and certainly the such hydrogenation also have the advantage you don't have an aqueous workup. The product is cleanly delivered and isolated after evaporation of the solvent, and the solvent then can also often be recycled, which is certainly an advantage for cost-effective production. Bayer was also aware that we are the only one that has this Crabtree Pfalz type iridium catalyst in our commercial catalog. So there are three complexes commercially available in the catalog, but we also from the research collaboration with the Pfalz laboratory, we still have derivatives. Professor Pfalz in the meantime retired. I was very happy to hear about that story, that this type of catalysts now really make it to the market and are used on scale. To give you an overview how this project evolved over the time, there was an initial route. I will start with the initial route that was also already there. Then the vision of the catalytic route, state of the art. So everything in blue you see here was solely done by Bayer. everything you see, or by the Licard Rostock actually, the ligand customization, everything that's in green was then done by Solvia's labs, or when it's both colors in close collaboration. So they had a vision of developing a catalytic route to make actually this herbicide available to the market. It's a herbicide used for soil protection. So they had this vision for catalytic route, then approached us. We did the first expertise screening for lead generation. Then the lead selection and optimization was done, and able to go to S2C of 1000. And then with the commercial available Uber Fox type catalyst. And then catalyst customization at Licard Rostock, enabled to go to S2C of 10,000. However, reaction time was more than 40 hours, which is a disadvantage. Then process optimization was done at Bayer and at Solvias, and this then enabled the first scaling of the asymmetric hydrogenation on 1 kg scale in an 8-liter autoclave here at Solvias. In parallel, then started also the iridium complex synthesis, since it was a customized ligand, not available on the market at all. The first investigation in the route enabled then this 1 kg production. There was Suzuki coupling involved to produce the backbone. This was done by Bayer. We did develop by another high throughput screening on our robot, developed the asymmetric transfer hydrogenation to set the stereocenter, the chiral alcohol ketone hydrogenation in the backbone of the ligand. And in the meantime, this catalyst now is produced on multi-kgs and enables the multi-ton production of this herbicide on scale at Bayer. Yeah, we'll start with the first 2 points where we start. What's the vision? So in pyrofluxam has this structure here made of these 2 building blocks, key building blocks, and yeah, I will solely talk about key building block A, this chiral aniline here. And the original route was starting this, so this olefinic quinoline, dihydroquinoline, is actually directly available by cracking an oligomer that's used as an antioxidant in rubber. So this is very well accessible to a very low price. Then first the acetylation, and then a heterogeneous hydrogenation gave the racemic material, ring contractions, then delivered the aniline as a racemic product, and this resolution by a diastereomer salt formation with steatotartaric acid, then enabled actually to get to the chiral building block, however much less than 50% yield. They also then looked into recycling the undesired enantiomer from the mother liquor by adding NaOH, and then at high temperature on palladium on charcoal, more than 180 degrees, and repurification, they could recycle it to some extent. However, this was not economically feasible on scale, much too expensive, too much input, many waste streams, aqueous waste streams. Yeah, this was not a solution to their problem to make this herbicide. And then the catalytic route, certainly you can think about just do an asymmetric hydrogenation of this olefin. You can think about doing that on the acetylated stage, or on the first stage also with the free amine. And this was then the point where Solvias came in. And the initial state-of-the-art results were already published, as mentioned in the patent application. Very low conversion, very low EE reached. They looked also at other metals, ruthenium, rhodium. Iridium Uberfox was then the most promising, so the Solvias ligand on both actually, but both very low conversion, low EE. So that was the point where we then came in with the expertise screening and followed by the lead selection. And we did a high throughput screening, 96 well plate for both substrates. We put on all the few Crabtree pulse type iridium catalysts that were available in our library, certainly a bit focused on the commercialized ones under different conditions. We also still also considered in the screening other metals, to possibly get a lucky hit there. 6 solvents were tested in parallel, 4 additives, overall 32 catalysts. At 4 more %, we usually scale at quite high catalyst loading to not miss a hit, since the first target is always to assure an NC selectivity to get a lead, and from there then the optimization is done. And with that screening, we get quickly then interesting leads. We found actually that one of the commercially available complex gave reasonable EE and full conversion. However, then it also showed clearly, the screening showed that actually the acetylated compound could be very well with the complex SKX003, actually with the required EE and with full conversion after reaction overnight in TFE. So a highly polar solid, fluorinated solvent gave then the desired result. But that's at 4 more %. So next step, certainly lower the catalyst loading, what we have to do. And this was done also at Bayer. And they found, well, we can go lower in TFE than other solvents were tested. They switched to HFIP, so hexafluoro isopropanol, and they found, yeah, we can go down to S2C of 1000, so 0.1 more % catalyst loading at the temperature, with reduced concentration, and achieve a conversion overnight. It's reasonable. Also EE just slightly dropped to 97. However, then further going down with the catalyst loading was not feasible on complete conversion. And this then is when Bayer approached Likat Rostock, the Bella lab, for the catalyst customization. So Bayer provided this building block, or different building blocks, and a Suzuki coupling then enabled to functionalize in the 2 position, and deep protection variation in position 4 was already provided, and then addition of a base, phosphorylation, and then iridium complex formation gave then these different complexes, and they tested that on activity. Was also published, as you see at the bottom, in OPID, and actually also then patented. And they found actually in the 2 position where the most active catalyst has a di-auto difunctionalization and the methyl group in the power position. And what that screening also shows, or this ligand variation, is that just like very slight changes in the backbone lead to a significant influence on the catalyst performance, like methyl groups or isopropyl groups in the auto position. Power position already shut down the reaction. Even then gets worse when you don't have auto substituents or electron restoring groups, or very small substituents as a methyl group. 4 position was found that the methyl group works best of the derivatives tested. Phenyl group doesn't work at all. And on phosphorus, actually, it was shown that cyclohexyl is very competent, and even more competent than the one that is on the available commercially available catalyst, the Herzbutyl group. Other phosphines didn't work that well at all. But with that, a more active iridium complex was found, and at Likat they already could show, well, now we can actually do S2C of 10,000, and now it becomes economically interesting. 17 hours reaction time. Well, not complete conversion after 40 hours, still not complete 98%. So we are certainly here also hitting a limit again at S2C 10,000. And then actually additive screening was done, and adding BF3 ether rate then was the solution here, enabling then at an S2C of 10,000 after 16 hours reaction time full conversion. And these conditions were then scaled at Solvias. We added even less additive at S2C 10,000, and the hydrogen uptake curve actually showed, well, after 4 hours the reaction was finished. This then enabled further. We're also switching to a production autoclave, enabled to go to S2C 25,000 in the following, which was then done by Bayer. So we did a 1 kg production at our site in an 8-liter autoclave. HFIP is quite rather critical in handling, but we can do such chemistry. At Bayer, this is then really in a closed facility. They are also recycling the HFIP since also due to cost. And our experts, actually Hans on the right side, he is working more than 50 years for Solvia, so he's highly expertise in autoclaves, what kind of gases, and yeah, he actually was involved and is highly motivated still. In the meantime, he retired more, but still coming in once a week, giving then input. Not involved now in production anymore, but a few years ago he really was still involved in that project. Yeah, and from there, well, we showed it's feasible on 1 kg. We can scale it. Now the question is, can we also make actually the iridium complex? How we can synthesize that? And there was just an academic route available at that point. It started actually with an early stage Suzuki approach. So we has also investigated together with Bayer, also different approaches with the late stage Suzuki, which has some advantages when you can do the late stage transition metal catalysis. However, it turned out then that this route was still the best with the early stage. However, at that point, expansive catalyst with quite high catalyst loading was used. Chlorinated solvent was used for the oxidation. A lot of waste produced. Acetylation, also large excess. Chromatography was necessary after acetylation. After hydrolysis, also chromatography. Swern oxidation was starting at -78 degrees. Chromatography was necessary on larger scale, less than 50% yield. So several challenges. And then the asymmetric reduction of the ketone to give the chiral alcohol. Actually, there was no efficient method reported. No catalytic method reported at all. And this then was the focus of the catalysis team. In first investigation on the route, then by our ligand group and process chemists, critical parameters were identified together with Bayer, and the goal was really to eliminate here the non-scalable process and steps. And mainly focused on chromatography, lower catalyst loading, and price. And this first route scouting then delivered the first grams for this 1 kg hydrogenation that I just showed. But from there it was taken up and the route was developed. I now focus here on the asymmetric reduction of the ketone. Requirements at that point were that we have a cheap and sustainable primary reductant. Hydrogen certainly most attractive. However, pressure equipment is necessary, and actually the availability for this, like in that range 100 kg to 1000 kg, is not that well available on the world market. So transfer hydrogenation also appeared to actually quite very attractive option, where you then have formic acid or formic acid salt as a reductant source. Goal was reasonable low catalyst loading, around 1% or lower, very high enhancer selectivity in the backbone, and that there's no column chromatography. Certainly, it's kind of challenging to always make a ligand backbone. It can be challenging since actually the product that you make also has a chelating character to the metal you are using, and might actually shut off and knock off your ligand for the active process. And here, high throughput screening, much more options here available on asymmetric transfer hydrogenation compared to the screening with the Crabtree Pulse type iridium catalyst. So 12 isolated ruthenium complexes were scaled, 15 ligands with 3 ruthenium sources, different hydrogen sources, 6 different solvents, and conditions here we started a bit lower, 2%, but still reasonable high to not miss a lead. Under these conditions, which are literature now. And here you see, we know much more about that chemistry from academia, but also industry. Our library has many examples of asymmetric transfer hydrogenation we developed for our ketones, so we get many hits actually. And these leads are then also tested and optimized on laboratory scale. Certainly also economically factors came in, so we test this then on laboratory scale, 0.5 gram, 1%. And we then do IPC taking, So in process control, taking aliquots, we see actually, yeah, the tethered DS-DANAP ligand is most active after 0.5 hours already, full conversion. And this was then further refined, was found in ethanol, it's much faster. And in acetonide trial, it was a bit slower, but higher EE, even higher EE was reached, and loading could be lower to 0.5 mol%. So this is then the refining that's often done after initial lead identification. And with that, we had an interesting system. That ruthenium catalyst is available on the market, so we could run that. But yeah, so it's not only catalysis, and the requirement was still we don't want column chromatography. Now the challenge was this alcohol really showed a low crystallinity as the enantiomeric pure alcohol. So then our process experts came in, and our solid state experts that then quickly developed actually isolation as a salt, as a camphor sulfonic acid salt, and this delivered then the pure compound 94% isolated yield over 99% EE without column chromatography. In the meantime, also the other steps have been optimized by Bayer and Solvias and ready for scaling. So a commercially attractive ligand for this quite challenging Suzuki with a highly sterically hindered coupling partner was found. It was found for the oxidation that there's no additional solvent needed, acetylation also no additional solvent, and much more concentrated possible. Was found at this stage crystallization can be done in isopropyl acetate, and oxidation was then switched to a tempo system, delivering then the ketone in 99% yield. And then, yeah, the last step I just showed, purification as salt first, and overall yield was then 68%, and 3 simple solid isolations in between. Yeah, and then the end game, although there we are highly experienced with phosphine chemistry, as you can imagine, the ligand group. So phosphorylation after N-Buli deprotonation, and then iridium complex formation with sodium bath directly leads to complexation and then crystallization of this iridium complex, which is also reasonably air stable and has this beautiful red crystalline color. And this, in the meantime, is now scale up on multiple kgs. Yeah, with that, I think that project nicely shows how a collaboration between industrial partners, but also academic groups, can lead to success. This catalyst customization is certainly something that takes time and takes someone that takes a longer look, and this is done in academic groups, and they are also interested in this interplay between different backbones and developing new chemistry, and then this is optimized and now running on ton scale. So at a SC 25,000, quite concentrated, short reaction times, and optimized in a loop reactor. Instead, the sustainability gains by introducing this homogeneous asymmetric hydrogenation are quite significant. So from the first generation to the second generation, the PMI drops by 70%, energy consumption drops, and also the CO2 equivalence drops by 45%. And now, we have a sustainable production of the herbicide on scale. So it's not only economics, it's also environmental impact, enabling a green process. With that, I come to the acknowledgement already. First and foremost, we, the Catalysis team and the ligand team and the process team at Solvia, thank the Bayer Crop Science team. Driver of this project was certainly, to mention foremost is Christoph Schoters, who initiated and led the project. also initiated their collaboration with the Likat Warstock, with Katrin Jung and Matthias Beller, that enabled then to really get from S2C 1000 to S2C 10,000, and then bring this this project to fruition. Now the iridium complex is produced by our ligand group here in Basel by Solvias. Yes, with that, I think we can close, Claire. I have additional slides if there's still time, but maybe we can first see if there are additional questions. And then I certainly can also talk about a related topic. That's about the other trend in transition metal catalysis, which is earth abundant metals, other ways to reduce the price of a process, or to also actually have different reactivity in your process.
Great, thanks so much, Akim, for a very interesting presentation. We do have some questions, so if we perhaps take those first, and then if time, we can go through your additional material. So the first question I've got here is, could you comment on why the pyridine ligand was optimized and not the serine-based oxazolidine series? Did you ever screen that detailed around their core structure?
The epox ligand probably is meant by that ligand, or so oxazolidine iridium based. So we screened these complexes, right? Also, but none was as effective in the lead generation. It already appeared that the iridium Uberfox type ligands, or this also called Crabtree pulse type ligands, are most competent for this substrate. So we didn't saw any activity in the initial screening on this type of ligands or catalysts.
Great, thank you. And could you comment on the utility to design a chiral ligand needing chiral catalysis for the making, as opposed to using the chiral pool?
Yeah, I think chiral pool is nice if you can use it. I mean, people also try to use it often because it's quite attractive, right? Chiral pool also can mean, not every natural chiral molecule is cheap, right, and accessible. And then if it's, we have here highly tailor-made backbone, then it can become quite challenging actually or also either impossible or too expensive to use the chiral pool. And then we basically show how you also can apply then high throughput screening and expertise in this area, or that has been already developed to then enable the access to the chiral backbone.
Thank you. Can you please comment on iridium recovery?
Mm-hmm. That's definitely that done, or intended to be done often. It depends on the catalyst loading, right, and how it can be isolated. But usually after then removal of the product, removal of the solvent that's also recycled, actually then iridium recycling is definitely possible. What's actually also interesting with this type of iridium pulse type catalysts is that they are quite stable. Actually, I was working as a master student in the pulse lab, and there we had a project where we isolated these type of ligands. But basically what we did is column chromatography to isolate them under nitrogen, right? And if you have such a low catalyst loading already, it's probably not worth it, but it works. So you can do a column chromatography, re-isolate the iridium catalyst and can use it again as a catalyst. But usually that's, at this low catalyst loading, it's more expensive than just do the iridium, the sole iridium metal recycling.
Thank you. In the AH screenings, do you make use of in situ catalysis, or are the iridium complexes prepared beforehand?
So we use both in that in that case. Where it's really the combinatorial approach that we use is really powerful. Like when you work with the diphosphine ligands, already more established ligand classes. There are so many derivatives available, and then this combinatorial approach is very powerful and also very well known and investigated. So we know the tricks. We have metal sources that we can use. We also use actually the in situ formation. Also on that screen we used it, but many of these pulse type ligands are actually isolated best and most as a iridium complex, and they are more stable and easier to purify, so they can easily be crystallized, as opposed to the PON ligand. Can also be isolated, but it's not as stable also on long term. So it's rather rare to use this combinatorial approach. In contrast to the chiral phosphine or mainly diphosphine ligands, actually that are often applied for many asymmetric hydrogenations when the substrate is not as challenging, so unfunctionalized and not that hindered.
Does the counterion of the catalyst play an important role for enantioselectivity?
Actually, it was investigated by the Bella Lab to some extent. I forgot actually to mention that at this point. So they looked at, do I have it here? Oh yeah, there you see they also looked at aluminium triflate and PF6. They found, you see here conversion is lower, so the BAF was found to be the most effective. This was already, more or less, it's already known from academic papers from Wald, Anderson Lab and others, that usually that BAF counter ion is the most effective in that type of chemistry.
So a related question to that BAF. BAF is quite an atom-rich counterion and has been around since the 1990s. Is there nothing comparable and more economic emerged since?
Mm-hmm. There might, I mean, I can't exclude that. There might be something around. This is still the industrial standard. It's also available on scale. So that's always also quite important. In an industry, you have an established process, you have an established chemical, it's available, right, and has been already scaled, and is usually then also price attractive when it has already been done. And something in academia is developed that's new, might be as good, right? It's always a hurdle then to switch. So you really need good arguments, usually on the price, right? Even more than just on the economy or on the weight of the molecule to introduce then a new one. But I mean, it happens from time to time, and I won't exclude that. Certainly also when you consider fluorinated compounds are considered more and more problematic, right, in having an environmental impact. Usually not a problem, when looking at such a process, they completely are working in a closed environment. They recycle their HFIP. The BAF is also not like getting out of the process. But I think there's definitely potential for improvement, and why not? I'm not aware really now if there's a more attractive solution environmentally, for example, but maybe not as price attractive. So can't exclude that, though there's certainly potential for improvement there.
Thanks. So one of the questions I have here, I think you've just answered. He's asking if the HFIP is recycled at the end of the process. I think you just said it is.
Yes, definitely. Also due to costs, but also certainly, also has an environmental impact. Yes, it is recycled.
Thank you. Can you expand on the main challenges faced in the scale-up for industrial application?
So challenging for the scale-up for industrial application. I think it needs to be, for catalysis, it needs to be a robust system, right, that can be applied. We don't want a glove box chemistry. We can't work with glove box catalysts or ligands that are very sensitive or too expensive. So I think it's a price thing. Catalysis can also be great in regard to safety considerations, right? When you do classic chemistry with highly reactive metals in quantitative amounts, such as Grignard chemistry, there's really a huge part of your cost is also regarding safety. Besides the big aqueous workup. In contrast, when you do transition metal catalysis, you just have smallest amount of highly active chemicals. And usually then the risk and risk mitigations are not as high.
Thank you. Can the iridium catalyst be used in transfer hydrogenation processes as ruthenium catalysts do, or do they only function under pressure?
So there are iridium catalysts that work for asymmetric transfer hydrogenation. I'm not aware of if the pulse type ligands have been tested for that. So it's possible that there's literature on that, or that someone tried it and published on it, but I'm not aware of it, that type of cationic ligands has been published on asymmetric transfer hydrogenation.
Okay, thanks. And for the imine reduction, what pressure of hydrogen was required?
Oh, that's a good question. I think it was rather low. Maybe I can figure that quickly out. There I probably would need to consult Felix Spindler, our consultant, to develop the process. I think it was around 5 bars.
Don't worry, we can look that up and send the answer.
Need to look that up in what they use in the end. I mean, they often what's often done when a process is developed, right? We work at a certain pressure. Then when it's going to ton scale production, they switch to a closed loop reactor, right, where you have a different surface area of solvent to the gaseous phase, and then often it's also possible to actually adapt the pressure to some extent and lower it further. That investment in the equipment is lower.
So is the loop reactor an essential part of the conversion, or is it there for another reason?
Yes, yeah. It's definitely an advantage here. We are not experts in that, so this was developed by Bayer with our other expertise company in that area that then really focused developing this loop reactor. So it definitely then supports then further reduction of the catalyst loading then really on scale. So equipment plays a role, as already in our equipment for the kg production, also steering rate, and it's often top steerers, right? And the hydrogen is introduced through the steerer. That really a good mixing takes place. But the more you scale a process, the more important such factors become, and then there's also really dedicated equipment for this kind of hydrogenation.
Is there a hypothesis for why the ortho places in the aryl group need to be substituted, so not an H?
Yeah, I think they didn't really do mechanistic investigations there, or what's the reason for that. So possibly it's often the last step, but it shouldn't be too large. So when the substrate leaves the catalyst, right, in the reductive elimination, that it's then expelled better. But it's really fine tuning, right? So it's just such a small differentiation then leads with this type of substrate to much more effective catalysis. So it also kind of shows a bit how challenging it might be to do, like using, I mean, that's very trendy now, to using in silico or predictive tools or DFT calculations, right? To say you want to predict actually you have your substrate, right? You predict, well, which type of ligand you want to use actually in that case. But seeing just such a small change in the backbone can have such a significant impact shows the challenge actually then to realize that.
Most facilities don't have the capability to scale reactions up to 60 bar. So where was the reaction scaled up and to what scale?
So this is an ongoing process by Bayer, and this was not disclosed yet. So I'm the wrong person. I'm not sure if I can actually answer that question, or allowed to answer that
No
question.
problem.
So yeah, would there then take a look at the publications in this last publication actually that you see here by Christoph Schodes and S. Müller. They describe nicely actually the process. There might be that they mentioned already what scale it is, but it's actually an ongoing process now. So the rhodium catalyst is now really produced on scale on our side, and yeah, at the same time now it's scaled to ton scales.
Thank you. A couple of questions about machine learning. Are you using machine learning to optimize your catalysts, and what may be the future role of AI to design screenings?
Mm-hmm. Well, I think for to design screenings, it's quite interesting, like to have learning algorithms that then make proposals or see actually connections, especially if you have like a huge amount of collected data over years, that there are connections that even an expert chemist don't see, and that then AI can read it out. You can have a learning algorithm, or as another option, you have a learning algorithm that's looking at a certain set of initial screened conditions on a substrate, on a certain substrate, and then it basically gives you suggestions for a second round of screening or optimization. I think there we are there yet already. This is implemented. We have there also collaborations, so can be quite interesting. And yeah, we are considering that more actually as a tool for us chemists, that we are guided through, see connections that we don't see, that we don't miss any information, and then by that improve the quality and also the speed of the screenings in future. So that's an ongoing process. Now, about the prediction of catalyst ligands, it's also a process of high interest and ongoing. Actually, maybe can quickly share a few follow-up slide on that. Just need to see where I have that. So actually, Genentech and Sigman from University of Utah, they published last year in checks about that. And Survey has actually provided the Walphos ligand on such a atroposelective cross-coupling reaction. And they did a high throughput experimentation with the Walphos ligands that are available from our catalog, and then they did based on that a statistical modeling to basically suggest more productive ligand, right? And then they requested a few ligands with certain groups on the phosphines, and we developed these ligands and then delivered them out so they could test them, and then did fit them to the statistical model. And interestingly, yeah, the statistical model fitted, like their prediction for the most productive then variation was fitting and really giving better results in this atroposelective cross-coupling reaction, which can be highly challenging, this Negishi coupling. So especially that substrate has a quite low rotational barrier. So quite nice paper in checks from Genentech and Sigman there. That's probably worthwhile to read in this direction. But as I said, I see it as still a highly challenging field to be fully implemented. But I mean, yeah, the algorithms get better, the computers, what we know, get better, right? So I can't exclude that that's really also a future application that might be interesting to follow. But it's hard to compete with the quite effective screening and all the ligands that are already available. And certainly that's always the first interest of customers, get it quickly to the market on an already scaled ligand. But I've seen there are cases where it's necessary to investigate, and if you can have an AI supporting your process, getting quicker to your solution, don't need 5 years, maybe just 1 year, right? It might. I mean, this would be a huge leap forward, right?
Absolutely. Is Solvius also active in developing earth-abundant metal catalysts?
Yes, so I also have here a few slides actually. So what we at the moment quite interesting, yeah. So we use different also earth-abundant metals, and yeah, there's this argument about motivation is price, right? Depends if you can really develop a highly active iridium or rhodium ligand. You don't care at one point, or the price became such a low part of your whole process that it doesn't play a significant role, and only that metal can do that, right? But here you can see the prices, right, of the earth-abundant metals, and on the right side are actually kg prices. And yeah, these are rates, right, not molar. So when you think about molar rate, it's even lower for the earth-abundant metals, much lower than for this. So this makes them more than tenfold less expensive, like a cobalt, for example, as rhodium. But I think the main motivation for us chemists, since we can develop these other ones, is actually reactivity, right? Expand the toolbox, get a late-stage chemoselectivity, do certain combinations, or then a motivation is also toxicity. And we are active in that field. We, yeah, there are certain challenges associated, like with for example, cobalt as a replacement or expansion actually to the rhodium catalysis. And with rhodium, you can start right away from an available salt, form active catalysts, or also form cationic catalysts or commercial sources of rhodium. Easily combine them, screen different ligands on your substrate, and then get an effective hydrogenation. But with cobalt-2 salts, this was difficult, didn't work well, so there was no effective method actually to make cobalt zero, in particular in zero. And Shirik published on that. Yeah, quite interesting, several papers, other than other groups. And they found actually that zinc is quite an effective reductant, maybe not the most attractive, since yeah, it also leads to reductions, but was found that this gives actually dimers, cobalt-1 dimers or cobalt zeros, active hydrogenation catalyst for example, enamide hydrogenation. And Shirik, then what they did, they isolated this complex A or B, focus on different phosphine ligands. That's for new BP. That's, for example, highly nice ligand, very perfect chiral environment around the phosphine, highly flexible backbone, but it's quite expensive and it's glove box catalyst. So it's interesting from an academic point of view to investigate that. So they could also get amazing results also here in such a commercial asymmetric hydrogenation to give a chiral amine. In the screening, where they added in situ zinc to form the cobalt complex, they actually also found that some of the Solvius type ligands were quite effective, and in particular, Jasperphos ligand gave one of the highest EE. So we are looking in that field. We are also interested in hydroformulations and hydroborations, hydroacylations that have been disclosed by other groups. And for us, the main focus is actually that we can quickly do a combinatorial screening with this cobalt-2 salts that are very low priced, add an organic reductant, add a diphosphine ligand, do the selective reduction, remove all volatile byproducts of this reduction, then get competent cobalt-1 or then cobalt-0 or cobalt or a cationic cobalt catalyst, and then we can apply them with all these many ligands very quickly, very effective, on our screening platform without having like another metal like manganese or zinc in our solution that might lead to problems with certain substrates. So that's one area. Here I have also quite interesting inside secondary phosphine oxide, the Chorsper type ligands. They can have this secondary interaction by the P, while a phosphine or diphosphine ligand doesn't interact that much with functional groups. Like a secondary phosphine ligand can have this secondary interaction and then be also directly coordinating not only to the metal but also to the substrate. But even more, it's known that secondary phosphine oxides can actually directly act in the catalytic cycle, like set up for the splitting of the hydrogen, but also then deliver not only the hydride to the substrate, but also then deliver the proton, for example, in this hydroformylation shown here. This was already found in the 80s. It's also kind of related to the Noyori transfer hydrogenation bifunctional catalysis and all these catalysts, manganese based and so on, that are based on that. We are also active there. And amido complexes, hydrido complex, they really enable that type of chemistry. And Ackermann, for example, found with the Chorsper that they enable this hydroarylation, hydrofunctionation of an terminal olefin and enable then this hydroarylation here. And they really found that these are much more active. It's a nickel-based catalysis, much more active compared to the classic diphosphine ligands. And they then did a follow-up mechanistic paper where they really showed, well, the ligand here is really active. They were living in hydride, and then making this kind of CH activation chemistry, hydrofunctionalist chemistry possible. So this is now a nickel-based process, but also apparently with cobalt, that's a quite interesting ligand. The Josephus ligands are also able to, for example, do a amination of carbamates. This have been disclosed by also in collaboration with an academic group by Sorias a few years back. Selectively functionalized carbamates with ammonia or with an ammonium salt. This can then also be done in presence of an aryl chloride or aryl bromide, and this is like a prime example expanding the toolbox, right? You might be able to do then a palladium catalysis on the aryl chloride and nickel catalysis on the carbamate to have this functionalization also on a later stage. Apart from that, Josephus ligands are also used in copper hydride chemistry. For example, I worked on in the Barkworld lab. I think there's also some potential. There's still challenges to solve. Catalyst loading is quite high, but it's also due to the fact that academic groups always present a substrate scope, right, that has to be as broad as possible. While in industry, we really focus in our screenings on one given substrate, and then we really optimize on this substrate the best catalyst that's most active. So I actually think also with this type of chemistry, it's possible when you really dedicate the optimization to the given substrate that you can actually lower the catalyst loading significantly, and then do such quite attractive hydrofunctionalization, giving several stereocenters, adding directly to carbonyls instead of highly active Grignard chemistry, or then with the N-electrophiles, the reductive amination of olefins, which are quite abundant molecules. So quite promising chemistry. This I showed already. Atroposelective transformations were also the diphosphine ligands that we offer in our catalyst portfolio are quite attractive. So I think that's from my side.
That's
I think
great.
we are also over time.
Yeah, thank you, Akeem. So yeah, I think given the time, we'll stop there. There have been a tremendous number of questions, so I'd just like to thank everyone for those. If we didn't get to yours, don't worry, I will pass on your question and your email address to Akeem, and I'm sure he'll get back to you personally. So it just remains for me to thank Akeem so much for putting together this excellent presentation, and also to thank his company Solvius for the sponsorship. So as I said before, I will send an email to everybody with a copy of the slides and also a link to the recording in case you want to watch it again. This will be sent to you by email later today. You can also access this on our website in the archive area, so look out for that. So thank you ever so much for joining us, and we look forward to seeing you again for the next webinar, which is actually next week. There are some new ones being added to the website, so please take a look. And just finally, thanks again, Akeem. Good afternoon or good
Thank you
evening,
very much.
everyone. Thank you. Thanks.
Thank you.
Bye.
Bye.